Imagine a technology that could change everything. I'm talking computing, communication, you name it. And it's all built from these tiny, perfect little crystals. But there's a catch. One tiny, absolutely maddening flaw.
This right here is the hero of our story, the Perovskite quantum dot. It's a nanocrystal so small that it plays by the completely bonkers rules of quantum mechanics, and its potential is just enormous.
But this is the flaw, the big problem. It blinks. Just randomly, with no warning, it turns itself off. And if you're trying to build the future of quantum tech, well, that's a total deal breaker.
So what are these quantum dots anyway? Well, you can think of them like artificial atoms, really tiny ones. These specific dots are made from something called a perovskite crystal. And here's the cool part. When you zap them with energy, they light up with this incredibly pure, brilliant light. And that property, that's what makes them such amazing candidates for things like next-gen LEDs, lasers, and you guessed it, the core building blocks for quantum computers.
And the researchers behind this study, they don't mince words. They say this blinking and this other issue called photodarkening, it's ubiquitous. It's just everywhere with these things. It all comes down to these tiny little defects on the crystal surface, and for years this has been the Achilles heel of the whole technology.
Okay, think about it like this. The transistor in your phone, it has to work, right? Every single time. If it just randomly decided to turn off, your phone would be a useless brick. It's the exact same logic here. You just can't build a quantum computer or really any reliable tech with a part that's fundamentally unpredictable.
So to fix the problem, you first have to understand where it's coming from. And it turns out it all comes down to the quantum dot surface, which is, well, it's unstable and frankly, it's a mess.
All right, let's break this down. Why do they blink? First off, the surfaces of these crystals are just naturally flawed. And these little defects, they act like tiny traps for electrical charges. Now, once a charge gets snagged in one of those traps, the dot just can't emit light properly. It goes dark. And since this whole trapping thing is totally random, you get this flickering, this blinking, with no rhyme or reason. So for years, the go-to solution was to basically try and pave over these surface problems. The idea was to coat the quantum dot with these special protective molecules called ligands. You can kind of think of it like a custom-fit molecular jacket, right? Something designed to wrap around the dot and create this perfect, stabilizing shield. But the old ligands, molecules with names like DDA, they had a pretty fatal flaw. See these long, bulky, sprawling tails? They were actually designed for something else, to help the dots mix into a liquid. But when you tried to dry them out to make a solid device, well, that's when a whole new problem popped. And this quote really gets to the heart of it. The scientific term is steric repulsion. All that means, in plain English, is that those big, clunky tails literally get in each other's way. They push each other apart, and that makes it completely impossible to form a tight, seamless seal around the quantum dot. Here's a great way to think about it. Imagine you're trying to perfectly gift wrap a soccer ball, but all you have are big, square bricks. It doesn't matter how you arrange them, right? You're always going to have gaps. And in the quantum world, those gaps are the defects. They're what lets the charges get trapped and causes that dreaded blinking.
Okay, so if the bulky bricks don't work, what's the plan? This is where we get to the breakthrough. What if, instead of forcing things, you could design molecules that wanted to perfectly assemble themselves into a shield?
The secret sauce here is a cool chemical principle called pi-pi stacking. Basically, it's a special attractive force that happens between certain flat, ring-shaped molecules. So instead of pushing each other away, they're naturally drawn to stack together, nice and neat, almost like tiny little magnetic tiles. And you can see the difference clear as day right here. On the left, you've got the old, bulky DDA ligands. It's a total mess, leaving the surface exposed. But on the right, those are the new, sleek ligands called PEA. They use that pi-pi stacking force to just snap together, forming a perfect self-assembling shield. It's beautiful. So the theory is super elegant, but did it actually work? Let's look at the results, because this is where the story goes from a frustrating problem to an incredible, stable solution. And the numbers, wow, they're just staggering. With this new molecular shield, the quantum dots were in the on state an average of 98.6% of the time. The blinking was, for all practical purposes, gone. They basically solved it.
And it's not just that. They also became incredibly durable. These new dots could run nonstop for over 12 hours under a laser beam without darkening or breaking down. That is a huge leap in stability.
And maybe most importantly for the future, they achieve 98% single photon purity. Now what that means is that when the dot flashes, it releases one and only one photon of light. That kind of precision is the absolute holy grail for building things like quantum light sources.
Let's just put this all side by side so you can really see the difference. The old method? The dot was only on for, less than 17% of the time, and it basically died after 2 minutes. The new method? It's on almost 99% of the time, and it's stable for over 12 hours. This isn't just an improvement, it's a complete game changer.
So, okay, the blinking is fixed. That's huge. But the real story here is bigger than just fixing a bug. It's about what this solution unlocks. It's about taking these quantum dots from a cool lab curiosity to a reliable industrial-grade component that we can actually build the future with.
You know, for the first time, scientists have a stable, predictable platform to actually work with. Before this, the blinking and the degrading, it was like trying to listen to a beautiful song with a ton of static in the background. You could tell something amazing was there, but you couldn't really make out the details. Now, by getting rid of all that static, researchers can finally hear the music. They can study the true quantum physics of the dot itself. And this clear signal, it just opens up whole new worlds of research. Scientists can now study the real behavior of things called excitons. Those are the quantum quasi-particles that are basically the engine making the light. They can measure exactly how those engines interact with the crystal itself. This leads directly to designing better quantum light emitters. It means we can finally test our wildest theories against real-world data and actually engineer quantum materials, not just stumble upon them by trial and error.
So we've gone from a fundamentally broken component to a stable, predictable quantum building block. It's like a foundational piece of a massive puzzle has finally been snapped into place. And that leaves us with a really exciting question. Now that we have these reliable building blocks, how long until we're building the quantum internet?